Well, thanks again for joining me. Today we're going to be talking about radioactive decay. Mother Nature has a very strong preference for things to have low energy and to be stable. So things that have high energy tend to lose energy and give off that energy in the form of light or heat, and things that are very unstable tend to become stable by emitting either particles or radiation. So if we start with a very unstable uranium-238, what it's going to do is try to make itself more stable. And it can do that by emitting an alpha particle, and then it will generate thorium-234. The half-life of that first reaction is about 4.5 times 10 to the 9th years. So in actuality, uranium-238 is actually very stable. But then the thorium-234 that's produced undergoes a beta decay and turns to protactinium-234, and that half-life is a mere 24 days. The Pa-234 is extremely unstable, and it emits a beta particle to generate uranium-235 with a half-life of 1.2 minutes. These decays continue over and over and over again, alpha and beta decays, until finally you're left with stable lead-206. So all the big heavy elements are decaying down to lead, and it turns out all the light elements are working their way up to lead. Something about lead is very stable in nature. Alright, so we'll spend a little bit of time talking about this, and you'll get some practice writing some of these alpha and beta decay emissions as they go on. What you're looking at here is called the well, it goes by lots of names. It's called the island of stability, the peninsula of stability, the band of stability. And what we're looking at is number of protons versus number of neutrons. And if the red line that I've shown here is a 1-to-1 ratio. So it turns out that light elements, you know, those elements, roughly elements 1 through 30, tend to be more stable if they have 1 proton to 1 neutron ratio. Okay? So if carbon has 6 protons, it wants to have 6 neutrons or a mass of 12. That's stable. If nitrogen has 7 protons, it wants a mass of 14. That's stable. And then as you get heavier and heavier, you end up having to add additional neutrons to maintain the stability. When you get to the really big boys, you need about 1.5 neutrons per proton. Now, I grew up watching Andy Griffith's show, and there was a character in there named Andy, and of course there was his deputy, Barney Fife. And that's all you needed to maintain peace in Mayberry, was just those 2 law enforcement officials. Now, if it were in today's society and something bad happened, they would definitely have to call in the National Guard, wouldn't they? Or additional law enforcement for assistance, because you know, if you're small, you know, 2 police is enough. But when you get bigger and bigger towns, you're going to need additional law enforcement. So that's kind of how I think about this. Maybe a better way to think about it is what's really going on. The nucleus is a very small, what I'll call town to live in. And when you have a large number of protons in a small area, they're all positively charged and they repel. So it needs a buffer, it needs something to maintain the status quo, and neutrons tend to do that. Neutrons keep that stable when you have extra protons in the nucleus. So what happens is Mother Nature will cause a decay to occur in a way that the atom will move toward this band of stability, the black dots. Now what you're actually looking at there is if you go vertically up, you know, if you see 5 dots, that means there's 5 isotopes of that particular atom with that number of protons. And so the atoms, Mother Nature would like the atoms to be on that band of stability. This one shows a little bit greater detail. I can still see the 1-to-1 dashed line. And here's the half-lives. So if they are in black, they are stable, right? And then as you go to red, they're stable from 350 years to 46 billion. I think that's still pretty stable. So red and black are pretty stable. And then by the time you get to the green ones, though their half-lives are just a mere 1 second to 12 days. And the blue ones, a second or less. So you can see that the farther away from that black line you get, the less stable each of these get. And again, you can see all the terms we use for this. The island of stability, the sea of instability, the peninsula of stability. I think people just want to have their little name associated with it. This one is showing the black ones occur in nature, and the red ones are naturally occurring radioactive. Again, not a lot of important details there. This one, it's talking about alpha decay and beta decay to return to this band of stability. And I can show that better maybe on my next slide for you. Okay, so let's look here if we come to it. Nope, not that one. How about this one? All right, so we know carbon-12 is very darn stable, right? But if we get other things like carbon-13, it's not. Well, it's still pretty stable, relatively stable, right? But if we go to carbon-14, its half-life is 5,700 years approximately. If we go one more neutron to carbon-15, its half-life is a mere 2.45 seconds. We add yet another neutron, and now its half-life, its stability, is 0.75 seconds. If we go the other way and subtract neutrons, you can see we go from being very stable down to a half-life of minutes or seconds or even tenths of seconds. So Mother Nature definitely has a preference for which isotopes she wants. So now we're looking at a very, very small part of that band of stability. The black elements are stable and the gray ones not as stable. So look at how this works. Let's assume you are neon 23 up here. Okay? Right now you're not stable, but you're trying to get onto the band of stability. Well, how do you do that? It says it moves into the band of stability by beta decay. So I've written this out for you, and hopefully you understand how to write a nuclear equation. It says beta decay. So that means it's going to emit a beta particle, and then we figure out what it turns into. So let's add up the top numbers. 23 is 0 plus 23. Great. Look at the bottom numbers. 10 is equal to -1 plus 11. -1 plus 11 is 10. The element 11 is sodium. So neon 23 emits a beta particle and changes its identity and becomes sodium 23, and that's how it gets onto the band of stability. Okay, let's try another one. Here's neon 19. We're down here, and it's going to move on to the band of stability by positron emission. Now, please remember, a positron is a positively charged electron. So here's the neon 19 that we start with. It says positron emission. See, there's lots of words. Decay means it produces. Emit means it produces. So here's our positron, our massless with a +1 charge. That's not a proton. That's a beta particle or an electron with a positive charge. And now we add this up. 19, 0 plus 19. On the bottom, 10 is equal to 1 plus 9. So element 9 is fluorine. So neon 19 emits a positron to become fluorine 19 and joins the band of stability. That's what it's all about. Okay? That's why nature's doing this, to have the right proton to neutron ratio. This graphic is showing us how you can go from, I'm on the left over here, how I can come down to the band of stability. If I'm on the right, how I can get to there. Or if I'm too high, how I can get there. Through either beta, alpha, or positron loss or capture. Okay, lots of different ways we can make that all happen. I'm looking at here now, the bottom of the slide lists some kind of important information. It summarizes for you what an alpha particle is, a beta, a positron, gamma, a proton, and a neutron. All of those could be used in writing nuclear equations. Now, on the top, it's not animated, but you can imagine everything underlined. If it wasn't there, you could predict what's going to be there. Now, I've also used other terms. If something absorbs something or is bombarded, it means it's going in on the reactant side. If it says it's producing or emitting something, it's going to come out on the product side. So this first example might say radium-223 emits an alpha particle, and what other nuclide? That's a specific isotope, which nucleus, which isotope you have. So if I look at this, the bottom number, 88, equals 2 plus, well, 86. Element 86 is radon. Now as to how do I get the top number, 223 equals 4 plus 219, and that'll be the 223. You don't worry about the positive charge or the negative charge of that ion. That's not going to matter. Okay? Next one. This one might say if you take nitrogen-14 and bombard it with an alpha particle, you produce protium or H1, and what other isotope? So again, you kind of have to go through the math. 14 plus 2 is 18. We know this is a 1, so this number on the top needs to be a 17, so that it adds up to 18. On the bottom, 7 plus 2 is 9. We know this is a 1, so this has to be an 8 plus 1 to get the 9. And you can take the time to look at each of those. I believe they're all done correctly. Okay? And take some time to do that. I'm not going to read them all to you. You feel free to pause and go through that. All right, I'm going to keep moving. Now, there are different units we measure radiation in. It's unfortunate that there's so many different units, but again, everybody wants to have their little 10 seconds moment of fame. So there is something called a Curie that measures radioactive decay, and Madame Curie was one of the first people to discover radiation and do a lot of research with this. Henry Becquerel also did early work with it, so there's a unit called a becquerel. Wilhelm Röntgen did early work on it. His deals with exposure to ionizing radiation versus just radiation in general. There's two other ones. There's one called a rad, which oftentimes you'll hear reported in the news, has to do with the energy absorbed caused by ionizing radiation. That's stuff that's bad for us. The one that I generally focus on is a REM. It stands for the radiologic equivalent in mankind. Now, as long as you're comparing REM exposure to REM exposure and Curies to Curies, you're fine. Just don't compare a Curie to a REM. It would be like comparing a kilogram to a milligram, right? They're two different units. I'm not going to ask you a lot about the units, but perhaps some of you are going to go into a career related to radiology where this will be more important to you. That's just a photo of Madame Curie and Henry Becquerel and William Röntgen, just to kind of see those different people. They were real people. All right. This one is kind of a sad story. We are, I would say, as a country, maybe not friends with Russia. And we've had what was called the Cold War that supposedly ended, but it's really not ended. Vladimir Putin, their leader, has been around a very long time, and he was in the 80s kind of disgraced. Russia was disgraced as they lost the Cold War, and he's been trying to get back all the land and the pride of the Russian people ever since. And it is not a democracy anymore that we would recognize in Russia. And Alexander Litnikov, this individual here, and I've mispronounced his name, but he was running against Vladimir Putin for president in the election, and he was poisoned. And he was poisoned with a very rare radioactive substance and died like 34 days later. Now, he said on his deathbed that he believes he was poisoned by, or had, maybe not directly by, but Putin had ordered his poisoning to kill him. Now, here's another dose. It's called a sievert. And so if you get a sievert of less than 0.5 or a rem of 50, the only thing it's going to do is make you look like you're fighting an infection. Your white blood cell will increase. If, though, you receive between 150 and 750 rem, you're probably going to need intensive hospitalization if you are going to survive. At the high end, you're probably going to have all your white blood cells destroyed, your white blood cells forming organs destroyed. And if you can survive, it might take 1 to 2 months, you generally recover, right? If you are in the range of 750 or above, you're going to die within a few days to a month, and that's what happened to him. If you receive more than 1,000 rems of radiation, generally you don't survive the night. You're dead within 24 hours. Now, Levitnikov was evidently poisoned by putting some radioactive material that was smaller than a grain of salt in the food he ate at a restaurant in Paris. When he flew back to Russia, the people on either side of him in the airplane had radiation sickness. That's how radioactive he was given was. I'm not just making up this story. You can read about it. Russians in particular, that is their MO, their modus operandi. They like to poison people and then hold it over their head like, if you don't tell us what we want, you will die. If you tell us, we'll give you the antidote type thing, right? It's really kind of weird that is still happening. All right. In terms of, and I've mentioned this before, radiation is proportional to 1 over the distance squared. So if this is a radioactive source, it spreads out over a distance. So radiation, if we think of that as this evil beast here, we don't want that anywhere near us. We want to get rid of it, right? And so we want to be as far away as we can. If you're twice as far away, you get 1/4 the radiation. If you're 3 times farther away, you get 1/9 the radiation, 1 over the distance squared. So if there's a nuclear accident, the one thing you want to do is either run toward the light and die, or get as far away as you can and hopefully survive. All right, let me give you some examples here of alpha emission, beta emission, and positron emission, just so you can kind of see. So in the first case, I've given you alpha particles, and they are being emitted, right? They come off from the original substance. And you go ahead and, you can pause the slide, pause the video to watch and make sure they all add up for you on the top and the bottom. I'll next do some beta emission. Remember, beta particle is an electron, is 0, -1. And again, these should all add up for you. 13 plus -1 is 12. 27 plus 0 is 27. And then how we determine the element's identity is we look at the number of protons, the atomic number. And then, of course, I've got here some beta emissions, some positron emissions. These are positively charged electrons, and it works the same way. 7 plus 1 is 8. 14 plus 0 is 14, and so on. So that it all works out. All right. Let's keep moving. In terms of nuclear reactions, it was interesting. Ernest Rutherford, the guy that did the gold foil experiment, was the first person that recognized natural transmutation of an element. He found out that radium, which is naturally occurring, that's what's in the Midwest under your house, that's why you have a radon mitigation system. Radium will decay, producing alpha particles and radon gas. And radon gas, if you inhale it, causes lung cancer. And that's why you have, if you have a basement to your house and you have a sump pump, you probably have a white tube going outside your house, removing that radon gas. The first artificial transmutation of an element was also done by Ernest Rutherford, right? Where he took nitrogen-14, bombarded it with an alpha particle, produced here a proton, and let's see if we can figure out what else was produced. Bottom number, 7 plus 2 is 9. 1 plus, well, that's going to be an 8 down here, isn't it? Element 8 is oxygen. And on the top, 14 and 4 is 18. 1 plus 17 is 18. So besides doing the gold foil experiment, he discovers natural radiation, natural transmutation. He discovers and makes it artificially, observes this stuff. He was a pretty sharp guy. Then comes along Chadwick, and he's probably just trying to do what Rutherford did, right? Bombard an element. So he takes beryllium, bombards it with an alpha, forms carbon-12, and recognizes there's a missing particle. 4 plus 2 is 6, which is 6, but 9 plus 4 is 13. So he knows there's something that has a mass of 1 and no charge, and that was where the neutron was discovered. Then finally, fission, which is how we do nuclear power, was discovered in 1939 by Hans Strassmann. And here's what they did. They took some uranium-235, they bombarded it with, struck it with a neutron, They produced the daughter isotopes of barium-141 and krypton-92, and then they produced 3 additional neutrons. These additional neutrons then went on to strike more uranium-235, causing that nuclear chain reaction. And that was discovered in 1939, yet by 1945 we had 2 atomic bombs, and then we started nuclear power very shortly after. So this was a very important discovery. Now, sometimes you look at periodic tables, depending on how old they are, they have more or less elements in them. So here are when some synthetic or man-made elements were produced. Uranium is the last naturally occurring element. Everything after uranium is synthetic or man-made. So neptunium was made by taking uranium-238, slamming a neutron into it, and we made neptunium. It happened to be 1940, I believe, the same year that the planet Neptune was discovered. Plutonium was also discovered that same year, taking uranium-238, hitting it with an isotope of hydrogen called deuterium. And that made neptunium-238, and it generated some neutrons. That neptunium-238 then spontaneously decayed to plutonium. I believe 1940 was also the year the planet Pluto was discovered, or former planet Pluto was discovered. Americium, that's the stuff in your smoke detector, was made in 1944 by taking plutonium, bombarding it with a neutron, and it made americium-240. Obviously, americium was made in America. It happened to be made at Berkeley in California, and that's where many of these elements were made, out there at Berkeley. And so I show here curium. It was named to honor her. She did not make the element or name it. She would have been dead by 1945. Berkelium here and californium, and then we have others that I'm showing you here just to complete the list. All right, and that's where I want to stop for the day. So thanks again for joining me. I hope this makes a little bit more sense why Mother Nature has stuff be radioactive. It's trying to become more stable. Everything in nature wants to be stable. And I hope this helped a little bit in terms of you writing and learning to write nuclear equations, learning to write both when an atom emits a particle or it absorbs a particle. All right, thanks for joining me. Bye-bye.